Okay, so well, before we even start, oops, we're dealing with a new word here, field. Has anybody heard this word before? I don't mean grass field before anybody says it. Does anyone know this word in physics, field?
No. Yeah.
What do you think it is?
Like space and area where something is acting.
Mm, half marks. What do you think? Do you have an idea?
I don't remember exact thing, but
Where something is filled. Space or area
but
where that's
can you say
filled.
it's like
No, your first answer was better, so be quiet. Yeah?
it's like the area type thing of specific
Something
yeah.
physics. Yeah? Okay, so you not 100% sure what it is. So anyways, before we get to exactly what a field is, we just need to clear up some things first. So I know you know this from chemistry and when we did electricity, but electric charge is something which is basic to electrons and protons and some other particles too, which we won't really look at. And electrons are negative and protons are positive. So you know this already, but at least make note of it again that electrons are negative and protons are positive. But I think Lorraine would be very angry at you if you forgot this. As would I, but maybe more Lorraine, because you would have been doing this for one semester already. Does anybody know other particles which have a charge actually? So here we said electrons are negative, protons are positive, neutron, don't make Lorraine angry. Neutrons have what charge, Tacken? So no charge. So my question is, do you know other particles with a charge? No, anybody? No? Electrons negative, protons positive. Do we know other ones? No. It's impossible. Yeah? How does an ion have a charge?
I don't know.
How does an ion have a charge?
Because you get
Yeah. It has extra protons or electrons or whatever. But can we think of any thing which is not a proton and which is not an electron but it has a charge? No? Have you ever heard of a positive electron? No? You can look them up. They're called positrons. Positrons. They're positively charged electrons. They are quite rare. You don't see them in day-to-day life. But they exist. So anyways, for us, we'll just imagine that everything that has a positive charge is because it's a proton, and everything that has a negative charge is because of electrons. Okay? Nobody's heard of this word before? Positron? Not even a sci-fi show?
Maybe a Megatron.
Megatron? Yeah. Nobody watches Star Trek then, no?
I think Coulomb.
No? The Next Generation? No?
Coulomb.
Well, if you did, you would know that the android's brain is made from positrons. But that's your loss. Okay. Come on. Why are we stuck? Uh-oh. That was a bit of an egg timer. Oh. Right, here we go. Things are negatively charged and load in. Things are positively charged, pull on each other. This makes electrons and protons stick together to form atoms. Things that have the same charge push others away, they repel. And again, this from chemistry. Positive and positive, they repel. Negative and negative, they repel. But positive and negative, they attract. So again, just please make some short notes to remind yourself of this. So like signs do what?
Attract. You repel yourself.
Repel. And unlike signs
Attract.
attract. So write some sentences about that.
Like what?
I just said it twice. You weren't listening.
Nah.
You were daydreaming about
I'll
something.
spell it out afterwards,
Got that? Probably learned this in week 1 of chemistry.
Maybe before to see,
I know, but in chemistry, week 1, week 2,
Maybe, yeah.
yeah. So anyways, so far this is nothing interesting. I agree. Okay, so now onto the juicy stuff. So now we can actually say exactly what I mean by an electric field. So the simplest definition I could find is an electric field is a vector field, and now I'll have to explain what that is in a moment, that shows the direction that a very small positively charged particle will move when placed in the field.
Write that down.
Oh, my goodness, yes. Got it? No.
Why can't a negatively charged particle move?
Oh no, it will, and it can. It's just for the definition we use a positive charge. Yeah. So I need to explain what a vector field is. Can I go back?
Just grasp it.
Ah.
It's not like the vector and the scalar concept, no?
No, it's related to vectors, yeah. Yeah.
Okay.
Okay, so okay, a simple example to show what I mean. So imagine you have a wind blowing, and we'll put a wall here. So the wind is coming from the north. So who will feel more force? The person standing here, or the person standing here? And the wind is coming from the north. This one will feel more force. Okay, so you imagine that if you were standing here, you would feel a force this big from the wind. But if you were standing here, it'll be a smaller force. Here, I think it'd be like no force.
Yeah,
But when you're down here, what do you think?
more intensity.
More force. So if you were to draw the force vectors everywhere, what would it look like? Well, you would have big force vectors if you were standing here. Yes, yeah. And you would have big force vectors if you were standing here. But then here it gets a bit more interesting. Here you would have no forces,
Why?
and then, because you're right behind the wall,
Okay.
and then here the forces would get a little bit bigger. But then you also imagine that, okay, maybe the wind also curves a little bit here, or maybe it bounces a bit here, so you could have them going this way, but then they might start to straighten back up. And then once you're far enough away, it goes back to kind of the same thing it was earlier. So you see all these force vectors here, which show you how much force there is at a particular point. This is an example of a vector field. That's what I mean, or that's what we mean when we say a vector field. Like a field of vectors. So what do you think a scalar field might be, as an example? So here, the wind is an example of a vector field. So what might be an example of a scalar field?
Something that only has like a magnitude and
Yeah, but like give me an example. So here, it was wind, as my example. So, what would be an example of a scalar field? Any ideas? So it's like a vector field, except instead of vectors at each point, there's a scalar at each point. No ideas? Impossible? Dots of what though?
inanimate.
So what unit is that exactly? No? Alright. So here's your home, and here's your heater. So if you were standing here, the temperature would be 25 Celsius. If you were standing here, maybe it's 24 Celsius. If you were standing here, maybe it's 23 Celsius. So you could have, at different points, different temperatures. Temperature is a scalar, isn't it? So you can have different temperatures at different points. So this would be an example of a scalar field, where there are different temperatures at each point. Okay? So do we get the idea for a scalar field and a vector field? You understand what I mean? So give me another example of maybe like a scalar field or a vector field.
Light.
No, but tell me what you're measuring at the different points. So, like, what about something like air pressure? What would that be? What is? It'd be scalar. Air pressure, just atmosphere pressure. Would be scalar, yeah. And what about something like gravity? What I mean by is like the mass's weight. What would that be?
Gravity would be vector.
It'd be a vector field. In fact, it's not a very interesting vector field because it's the same force everywhere, same direction. Okay. Have you got this definition? Yeah? Okay, good. So this is a vector field, for example, when you have a proton and an electron. Now, in a later lesson, we'll look at more of the graphs, the diagrams. But to start with, this is enough. So you can imagine, if you're a positive particle and you're right here, if you're positive, which way will you want to move to? To the negative. So if you, KJ, were talking about the definition, we use positive particles as the definition. So if you put a positive particle here, there's a force and it'll want to push it like this. If you put a positive particle here, it will just shoot in. If you put a positive particle right here, it'll get pushed away and then pulled into the negative. So this here is the vector field, electric field, for a positive and a negative charge. Now, there's a different lesson where we draw the different diagrams here, but for this lesson I would like you to draw this. And in fact, in the exam, sometimes they actually say, draw the electric field for a blank. So for example, this would be the electric field for a positive and negative pair. You could also, you have other situations as well where you could have just a positive.
The levels, north and south.
Yeah, that's another lesson as well. Yeah.
I remember we did.
You draw them?
Yeah.
Yeah. So just for this lesson, I just need you to draw this one, please.
Probably is the most hated part.
Yeah, I agree. Okay, you drew this?
What should I call this picture?
Huh?
What should I call it?
Equals 0 point.
Calling an electric field. I just couldn't bother with a name, I just called it a picture.
Sometimes the levels.
There's 4 diagrams they can ask you in the exam. So this is just one of the 4. I think there's 4. But you kind of get the basic idea here that the field goes from the positive to the negative. You see that? Goes from the positive to the negative. Okay, can I go to the next slide? Yeah. Alright. So again, we talked about charge before. So we measured charge in coulombs. Yeah. So 1 coulomb is the standard unit here, and it's a unit of electric charge. And the definition is it's the charge you get from 1 amp in 1 second. So if you have 1 amp for 1 second, the charge that you get from this current is 1 coulomb. This is the definition of a coulomb. Okay. And it's a really big unit actually, because when you look at how much charge an electron has, it's like 10 to the minus 17 coulombs or whatever. It's very small, okay? But anyways, this is a definition which I've seen in the exam maybe like 5 or 6 times. You see, there's a few definitions which they like to ask in the exam. What are the other popular ones? I think one that we haven't done actually yet. Of all the definitions, this is the most common in the exam actually. The only other definition which would be as common as this in the exam would be, anyone want to guess?
Newton's law.
Well, the unit in Newton. So the 2 most common units that you need to define in the exam would be the Newton and the Coulomb. Do you remember the definition of the Newton? What is it?
The 0.
No, just the unit, the Newton.
Ampere.
Getting close.
The mass,
No.
the
Newton?
acceleration of mass.
Newton?
1 Newton of force is the force required to accelerate 1 kilogram of mass by 1 meter per second squared. Now you see,
I was getting there.
now you weren't. Well, you weren't getting there anytime soon. So the 2 most common definitions, Newton and Coulomb. So write the Coulomb definition down, please. You don't even need to say that it's an SI unit in the exam. Okay? I mean, of course it's an SI unit because all our units are SI units. Yes? Okay. So how big is a Coulomb? Well, for example, if you have a proton, now you told me you don't actually do this in chemistry, but if you have a proton, this is the charge of a proton, 10 to the minus 19 coulombs. Charge of an electron, the same. It's just with a minus.
Yes,
I would hope so. And second, what's the charge of a neutron?
I forgot.
No, you didn't forget. Anybody?
0.
Okay.
Neutron has no charge. You know this from chemistry, right? And also, if you want to know what the masses are, by the way, the mass of a proton is that much, the mass of an electron is that much, and the mass of a neutron is also that much.
You need to write them down.
You'll need them for some of the questions, yeah. Yeah? Got this? No. Yeah? Yes? Now, what might make this a bit more familiar to chemistry is often this charge of a proton or electron, we often can write it briefly as E, which is actually what's on your calculator. If you look at your constant table here, you can see that constant 23 is an E. This is the value 1.6 times 10 to the minus 19. So it's on your calculator as E. So think of E for electron. But it's also the same as a proton. And another way to write it, which is maybe what you see in chemistry, is just as plus 1. So
Yes.
in chemistry you would say the charge of a proton is plus 1 and of an electron is minus 1. So when you write quote plus 1, what you're writing is E, which is this number of coulombs. Okay? So just to try and connect this a bit more to chemistry, that's what's happening. So E on the calculator. And please don't confuse it with the E that's here. It's a different E. you need the E that's on the constant, number 23. Okay? Right. So if we continue. Now if I just go back to my picture here of the vector field, where was the field strongest here?
Beginning and the end.
Yeah, like here, if you were standing here or here, this is where it's strongest. And where it's weakest?
Just beside the-
Right behind the wall is where it's weakest. Yeah? So you have this idea that some parts are stronger and some parts are weaker. So this gives us the idea of like a strength. After all, imagine the positive charge. If I put the positive charge very close to the positive charge, will it move fast or slow? It'll move very fast. And if I put it closer to the positive charge, what should happen? You would feel like it would want to move away faster. Yeah? So again, just like with the example of the wind, different parts are stronger, different parts are weaker. So we have this idea of electric field strength, how strong it is in one place. So the formula for electric field strength, which we use the letter E, is the force per unit charge of the particle in the field. So basically the formula is that.
Equals for units.
The force per unit charge of the particle. Yeah? So it's a simple formula, but the idea, if the force is stronger, then we say the strength is stronger, basically. And the reason you divide by the Q, come on Fahad, wiki. The reason you divide by the Q is you want it per unit of charge. So think about this. Look, if you put 10 coulombs near a positive charge and you put 5 coulombs near a positive charge, which will experience more force? The 10. If you put 10 coulombs here, it wants to fly away faster than if you put 5 coulombs. So the reason we divide by the Q is to get the force per 1 coulomb. Okay? So basically the electric field strength is basically the same as the force, but it's just per charge. That's the only difference. Okay, so the units, what are the units here? Units?
Newton.
Newtons per
Coulomb.
Newtons per coulomb. Okay, so make sure you have this, please. Yep. Okay, continue. Yeah. Okay, so we have a current, and the electric field around this current is 10 to the minus 25 newtons per coulomb. But it's important that I tell you the distance, because remember in the picture here, if you're here, if you're here, the force is less than if you're here. So it is important that I tell you where you are. So this is the strength when you're 1 centimeter from the wire. What is the force felt on a free electron 1 centimeter from the wire? So I'll draw it here for you. What you have is you have a wire, and you have an electric field that's around the wire. Now I won't draw it properly because that's a later lesson, but we imagine that there's a wire and there's an electric field around the wire. So when the electron is here, 1 centimeter away, what's the force? Okay, so we use our formula. E equals F over Q. So F equals EQ. So the E, I tell you, is 10 to the minus 25. And what's the Q?
Charge.
Charge.
Yeah, but what is it here?
Charge of the electron.
Yeah, I tell you it's an electron. So we multiply by the charge of an electron, which is constant 23.
Why is it 10 to, oh, so minus 20?
I give you that in the question as the strength of the field.
So that means the distance from the wire, we don't use it in the calculation. It doesn't matter.
Well, it doesn't, but in a way it does, KJ, because it matters. Look, it matters that the electric field strength at 1 centimeter and that the electron is also 1 centimeter away.
Oh, so it just means that it doesn't matter that.
No, no, no. What I'm saying is it matters because you need to confirm that the electric field strength and the electron, they're at the same place. So like, for example, if I go back here, if I tell you the strength here, but I put the person here, or if I put the person here, it won't work. So I don't need it for the calculation. True. Okay, so the answer is 1.6 times 10 to the minus 44 newtons. Very small number. Fahad, come on. Wakey, wakey. No, 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 no. Keep the coat off.
Oh,
Yeah, keep it off. Because it'll just make you warm and cozy and sleepier.
the cold water.
Cold will keep you awake.
Oh,
It will.
Yeah.
Yes, it will.
cold.
You'll put your coat on and you'll go, ah. Okay, did you write this down? Yes, you did, yeah. No, you were asleep, so I'm not counting you. Everybody else, did you write this down? Yes, okay. So next example now. Okay, so you don't have to write all of it down, but you need to at least draw it. So you've got an electron, and it's 1 millimeter away from 3 protons. The 3 protons produce an electric field, and the strength is that. So again, KJ, I didn't need to tell you the 1 millimeter business. I could have just said the electron is placed at the same place. But anyways, what is the acceleration of the electron?
Acceleration.
Yeah. Okay, so can you at least draw this, put the numbers in the diagram, and then I'll do it. Okay, so just draw this for me. Did you draw it? Show me. Okay. Let's have a look here. Did you? I need you to write this number down. It's the strength of the field. Where is this at, this strength? On your diagram, where's this strength? At the electron location. Alright, so let's draw this. So you have your 3 protons, and then you have your electron here. What's the strength here? What did I say it was?
1.4.
Yeah? Times 10 to the minus 24 newtons per coulomb.
Minus or
Right, so we use our formula. E equals F over Q. So then F equals EQ. Do I want the F though?
Yes. So if you find F over
Yeah. So what law do I need to use next?
F equals M.
If I use F equals MA, I can make MA equals EQ. So now I can get the A is equal to EQ over M. Now, do you know the charge of an electron? You do. It's on your calculator. It is 23, the constant. Do you know the mass of an electron? You do. I give it to you.
9.11.
So if I put those three numbers in, I get an answer of 2.48 times 10 to the minus 13 meters per second squared. Now, do I need a plus or do I need a minus? Is this moving towards the proton or is it moving away from the proton? It's moving towards, and in the question I said use plus to mean inwards. So yeah, it is a plus. Okay, did you write this down?
Yeah.
Okay. Okay, so again, you don't need to write every word down, but at least draw with the information. So a small dust particle of mass 1 milligram and charge of minus 100 electrons is placed between two horizontal plates. The plates produce an electric field. The small charge is held balanced between the two plates and does not fall. How strong is the field at the point at which the dust particle is located?
We're looking for E.
Yeah, you're looking for E. So just draw it first.
Only one piece of this?
Yeah. Yeah. Did you draw it? Okay.
Did you put on the speaker now?
Sorry.
Speaker phone now ready? Changing the phone ready? Changing the dirt, the bottom and the battery.
Through that? Yeah? Okay. So, here, this is what you have. You have one plate, and there's another plate, and they make an electric field, but you don't care about the picture just yet. And there's a particle here. So, it's not falling. That must mean there are two forces on it. The first force, of course, is gravity, which is its weight. And the second force must be because of the field. Now remember that E equals F over Q. So how much is the force here? It's EQ. So that must equal the weight. So let's see what we get. EQ must equal the weight. So E must equal the weight over Q, which is equal to, what did I say, it was a milligram, was it? 0. Milligram?
Yeah.
0.001 times 9.81 all over the charge, which was 100 electrons, which is 1.6 times 10 to the minus 19. So you get an answer of 6.1 times 10 to the 14 newtons per Coulomb. Got that? Yes? Okay. A proton and electron are fixed 1 millimeter apart. What is the field strength at the point which is equal distance between their centers? So what you have here, you have a proton and you have an electron, and they are 1 millimeter apart, and equidistance between their centers means here. So my question is, what is the electric field strength here? So I'll give you a minute to try and calculate this. I want to know how strong the field is at that location.
What's your information?
Huh?
What's your information there?
I think I drew it all really. That's all the information.
Do you have to use the weight?
No, you can imagine that you're looking from the top. Fahad! Wake up or get out! And you're going to tell me you didn't have breakfast as well. Keeping quiet, good strategy. You're learning things. We got an answer?
No.
No? You sure? What's Newton's first law?
MVH.
No. That's the third law.
MVH cannot, no.
That's the third law you were saying.
The object doesn't move unless when you put a bat on it.
Okay.
Second one.
Right, that's the first law, right?
Yeah.
So an object is at rest or constant velocity unless acted on by a force. Now, if I put that particle, or sorry, if I'm between the 2 points there, the proton and the electron, which way would the particle move? That red dot. Would that red dot move to the left or move to the right?
To the right.
If you do what?
That red dot. Which way would it want to move?
In the middle.
The middle.
What do you mean?
The red dot is
White nose.
Well, yeah. Well, firstly, if you're in the middle there, you have a positive charge to your left, yes, and you have a negative charge on your right. So in total, there's actually no charge in the center there, because the positive on the left and the negative on the right cancel. Yeah. It's like if you had a force pulling to the left and a force pulling to the right, which way would it move? Well, if the forces are balanced, it won't move. So what I'm saying here is there's an electric field around the positive. So if you were to draw it, do you remember in the diagram here, it'll go out like this, and then there's an electric field around the negative. Do you know what? Actually, I think I made a mistake here. Yeah, I screwed it up. I should have said they're both protons. But you're going to pretend now that you could have done it if I just changed this. So if I make this a proton, now I could have done it. So imagine I put an electron in the middle there. Which way would the electron move, the red electron?
Move to the left.
Straight left.
Yeah, well, it wants to move to the proton on the left, doesn't it?
Mm-hmm.
But it also wants to move to the proton on the right. So which way does it move?
Nowhere.
It doesn't. Now what happens if I put a proton in the middle?
It will move to the left.
No, for the same reason.
Oh.
The proton on the left will push it to the right.
I thought you meant
And the proton on the right will push it to the left. So again, it won't move.
No, I thought you meant you put the proton in the middle when the electron is in the middle.
Oh no. Take the electron out, put a proton in. So anyway, my point is that because the F is 0, the E is 0 here in the middle. So in other words, the electric fields, they can actually cancel. So if you have two positives or two negatives and you're right in the middle of the two, it's like having no field. Because you want to move left and you want to move right, so it cancels. Yeah? So actually, let me just change that here. I should have said a proton and another proton. Okie dokie. Okay, they are your homework questions. No.
Do you want an answer to that?
Anytime today, just drop it into the office with the cover sheets on it. Make sure they're stapled.
Okay, I'll just
2 cover sheets.
The date should be today is the last one.
Huh?
Today.
The date?
I changed the sheet now.
Yeah, actually. Has anybody written the dates on their cover sheets?
No.
Make the date that it was supposed to be due on, please.
The 8th.
8th of February?
Yes.
The 8th of February.
Yes, the official date, please. That would be great, thank you.
I'll go to Sylvia now.
As you wish. Wait, there's still 60 seconds.